Okay, so Dean already told a number of things in his presentation last week that are also part of this presentation, which I will therefore happily skip when we get there. So this is a presentation I gave originally asked by relational AI, who are also interested in graph database technology. They're building a new system. They want to know what is the current state of the art in graph query languages. So I composed this survey with the help of slides from a number of people, notably Renzo Angles. So he is the first author of the survey paper that Dean was summarizing last week. But also Oscar van Rest, Oscar van Rest, a Dutch guy who's actually leading the efforts in Oracle to add graph query functionality to various products. Mingxi Wu, who is the CTO of Tiger Graph, which is a relatively new graph database product, and Stefan Plantikov, who is the query language lead at Neo4j. Okay, so here you see maybe I should minimize this a bit more. Sure, like this. Here you see a genealogy of, or at least a history time bar of the various query languages that have been proposed for graph data. And as you can see, there are quite a lot of them. So this started in 1987. I think I will get there. Alberto Mendelssohn proposed a language called G, the late Alberto Mendelssohn, of course. In the bottom below the timeline, you see the query languages that I will talk about, or that these are the blue ones. I will not talk about Sparkle, but these are the currently popular graph query languages. So Sparkle is, you can say, a graph query language if you think that RDF forms a graph, semantic web. But, well, that is a different data model. I will focus on query languages for graphs that follow the so-called property graph data model. And that was also what Dean was talking about last week. So these are directed graphs where the edges and the nodes can have key value properties, property pairs attached to them. So Cypher and Gremlin are the two most popular query languages Dean told you last week. I will also talk about a few more of these. pgql is the Oracle query language for graphs. GSQL is Tiger Graph's proposal for a graph query language. gcore I've talked about before, but I will shortly summarize that again. I talked about it, I think, like 1.5 years ago when we published this Sigma paper on it. gcore comes from LDBC, and you see LDBC also on the slides with its logo. So LDBC is a club of graph people, graph companies, originally for benchmarks, but LDBC is also venturing into graph query language design. And to the right, there are, in light gray, two graph query languages for property graphs that are, well, not yet popular, but they have been recently proposed, or they are in the process of being proposed by a standards community. So there is this new extension of SQL called SQL PGQ, which will likely be part of, it will be part of the next SQL standard, and that's then probably going to be SQL 2021. And the ISO working group is also working on a native query language, so a graph query language, not for the relational model, but for the property graph query data model. Okay. Next slide. Okay, so yeah, the very earliest history of graph query languages starts in 1987. Theoretical work, Cruz, Mendelssohn, and Wood. So they had a simple graph data model, and they had a query language that was both formulated in mathematical formal notation as well as in graphical form. And the main functionality of this graph query languages was pattern query and pathfinding queries. So here you see some of those examples, also the graphical forms of these patterns that then would be recognized in a directed graph database. So it is actually amazing, I mean, that it's already 30 years or 32 years of history of graph query languages, and so many different proposals have been out there. And for a long time, I must say, adoption has been slow, but well, property graphs are relatively popular. Although if you look at this slide, I mean, it's difficult to measure how popular these languages are really. Here I use Google Hits as some kind of proxy for that. So you can see that if you type in SQL query, then Google says 400,000 hits for that. And but if you type Sparkle query, then it's already down to 400 kilo hits, I must say, by the way. So it is already a factor 400 or 300 less than SQL, which I think is more or less maybe justified, because Sparkle is not that popular. SQL is way, way, way bigger. And Cypher and Gremlin are the two query languages that have most traction in property graphs. And they are, well, together they may be of the same order as Sparkle. So you could maybe see it like this. They are actually a bit lower still. There is a bit of fragmentation, so there's also Tiger Graph, and there's PGQL. PGQL has very little hits. So yeah, there are multiple systems that support these languages. So there's plenty of systems supporting SQL, and there is quite a few systems supporting Sparkle. Some of them call themselves graph database systems, like Amazon Neptune is a graph database service that's quite popular in the AWS cloud. But focusing on property graphs, Cypher was originally only for Neo4j, but they created something called OpenCypher, and they started pushing open source developers, but also other developers to adopt Cypher. And SAP actually did so, and as a commercial company, and there are some other companies, some smaller companies like Agents Graph and Enzo Graph that do so. OrientDB, which has existed for a longer time, an Italian graph database system, also supports Cypher now. And Neo4j also has this thing called CAPS, which is Cypher on Apache Spark, and this is a re-implementation of Cypher on top of Spark that is going to be part of Spark, Apache Spark 3.0. So it will be one of the standard interfaces in Spark from next year on. And then Gremlin originated in something called TitanDB, and TitanDB was an open source project led by Marco Rodriguez. It was bought by a company called DataStax, and that's called DataStax Enterprise Graph now. But somehow they also convinced IBM that Gremlin was a great idea. So that is called Janus Graph, the IBM version of TitanDB. And Neptune, so this Amazon service, also supports Gremlin. Stardog, which is actually originally a Sparkle system, also supports Gremlin. So okay, so it's different systems that support this, and some of them, yeah, are more than just open source projects. They also are kind of commercially supported. Okay, so that's kind of the landscape. And GSQL is only Tiger Graph, and PGQL is only Oracle. So what are the main ingredients of a graph query language? So what kind of functionality do they support? Graph navigation, so finding your way in a graph. You could say, well, graph pattern matching being part of that. So finding you kind of create a shape of nodes and edges, and then you have to find all the occurrences. Can be, as Dean explained, both with homomorphic and isomorphic semantics. Isomorphic means that all the things that you match must be different. Homomorphic means that the same edge or the same node can play a role in a binding that you find, say, at multiple locations for multiple variables. What you also saw in Dean's presentation, that the general idea of graph pattern matching is that you provide a graph pattern, and the system then efficiently finds all the so-called bindings. So graph pattern consists of a shape, but in this shape there are some things that are fixed that you ask for, like you may ask for an edge with a particular label, like person P, where P is a variable, then edge with label works for towards a variable C standing for company, or maybe with label restriction company. So P and C would then be variables, and these variables, they would be bound. So the system will find bindings. In effect, you will get a table of bindings called a binding table out. So it's graph in, binding table out in a way. That's certainly also the way that Sparkle works. Like Sparkle produces primarily tabular results where you find these bindings. But the same holds for Cypher, and the same holds for other query languages, pattern matching query languages. A more graphy, or even more graphy functionality is pathfinding, like shortest pathfinding or all pathfinding. Cheapest pathfinding is a version of shortest pathfinding where the edges have a weight, hopefully non-negative, positive actually weight, and then you're looking for the lowest sum of these weights. That would be the cheapest path in that case. You can just have simple clean star pathfinding. So clean star, I mean, like if you look for a path P, maybe a label like is friend of or something, and then you do is friend of star, and star meaning any 0 or more of those edges after each other. That is a very simple definition of path, but you can actually also have structural constraints on these paths. So you can use regular expressions like AB between parentheses star, or AB parentheses plus, and then C or something. You can do these kinds of things as well. That is, of course, a question. How do paths fit into the property graph? Later we'll get to that when we cover G-core, because a graph consists of vertices and edges, and doesn't really specifically talk about what the path is. And if you return paths, are they then also part of the data model? That's an interesting question. And in this graph navigation, there's also filters. And so graph navigation is to find stuff in graphs, paths or patterns. Maybe you find things, but after you found some results, you might want to construct or return something new. Well, maybe not a table, but maybe actually want to create a new graph, and then you can get to graph construction. And graph construction is intimately tied to grouping, actually. I'll try to explain that when we go to G-core. But graph construction also concerns how to extend graphs, or to merge new elements into graphs, or to say, okay, I have multiple graphs, maybe I find connections between certain vertices, and then I want to kind of union those multiple input graphs into a single output graph. But on top of that, it should also be possible, or it's conceivable at least, that you do not do only purely graph related things. You might want to do joins, inner, outer, anti-joins. Because, for instance, in these graphs you have properties, like you have maybe a property name or a property telephone number, and then you can also look for, you could be interested in, nodes that have the same name or the same identifier. That's effectively a join condition over your graph. So the whole relational machinery is also interesting for graph query languages. So you could see them maybe even as a superset of relational query language, these graph query languages. So also union, intersection, and difference between multiple graphs, graph views. Well, that's of course only possible. I mean, a view is only possible if the result of a graph query, because a view is a query, would also again be a graph. So for languages that are graph in, table out, views do not really are not really possible. Like for Sparkle, there are no views in Sparkle because of this, because the result of a Sparkle query is a table, not a graph. But for those query languages where the query actually returns a new graph, you can view those queries as views, and then you can build recursively queries on top of each other. Same holds for subqueries, by the way. So a subquery also supposes that you return, well, the query returns something that the query language can again work on. So if the graph query language supports returning a graph as a result, you can also have subqueries, and these can be simple subqueries or they can be correlated subqueries. And this is a terrain that hasn't been researched so deeply yet, because correlated subqueries, well, can be kind of complicated, and in graphs they could be even potentially more complicated. And there's also updates, finally, so deletion, insertion, and updating of graph data. So that is a sketch of, well, the functional panorama that is relevant for graph query languages. Okay, so I was part of the team that developed a graph query language called Gcore. So that was done by one team from the LDBC with people from the various companies listed below. So it was not only academics. We had some very smart academics, not me, but people from the theoretical computer science community, actually, who are experts in the well, more the complexity analysis part of query languages. So we try to make something that is actually functional and but also implementable. So that would not break the bank in terms of the complexity of the query language. So here you see actually this team, and the leader was Marcelo Arenas, and he is a well-known theoretical database theory person. So LDBC recommended this query language. We did not really want to try to create a standard. So I already alluded to that there are some new developments. So those light gray query languages, GQL and SQL. SQL GQL, how is it called again? SQL PGQ, sorry. These are attempts to make a standard. LDBC is not really in the standards business, but the ISO has a liaison with LDBC. So the working group who's working on these languages is connected to the original task force that's on the screen here. And IDs from LDBC are going to be part of those new query languages. That was the idea of the Gcore project, not to define a language, but to explore the ideas. So one thing that is, so here you see an example of the graph data model, of a graph data model like I think the G language had in mind. So that's just a directed graph where you have labels on edges and nodes, and then edges and nodes are the entities. They have an identity, so the identities in this example are numbers. So property graphs add the concept of attaching properties to both, well, to all entities, so to vertices and to edges. They can have key value pairs, as you can see here, like first name and last name and all that. Now the problem that, like I already told you, is that many query languages are not composable because they return tables, not graphs. We'll skip over that, so that means no views and no subqueries. But the other problem is, so even if you consider, okay, I want to design a query language that return graphs, then it would be closed under the data model. Query language that's closed means that you can have these, that the output of a query can be the input of another query. The second challenge is paths, because path querying, pathfinding is a very important use case that we also know from people who are actually trying to use graph data. Very often paths play an important role. But yeah, a language like Cypher, for instance, treats path as a second-class citizen, because a path is not really part of the property graph data model. Cypher kind of treats a path as, maybe a string or a list of identifiers that's just some kind of literal that is not directly relatable to the original graph again, or only through some tricks. And that means that paths have to be peeled out and iterated over in the client that actually gets the query result. But you cannot use the path as the basis of a new query. So what we thought in Gcore is to extend the property graph model, and we actually call it the path property graph model, because we add a third kind of entity, which is paths. And a path is a sequence of vertices connected by edges that actually have to exist in the graph. They have to have identities, and they have to be consecutive, or at least they have to be connected with each other, so they have to make sense as a path. And such a path can then also be part of a database, so you can create a database of paths. So you can think of trajectory databases that could be stored and represented in this model as well. And as they are entities, you can also attach then properties to these paths. And they can also have labels. So you can have a type of path, and they can have labels like this. And they can have properties attached to them. I think here there is an example where the label is to Wagner. I'm not sure what that means, but it has a property trust in this path. And so that is still considered a quite radical proposal. But it does mean that paths are now representable in the data model, and that your query can return graphs, but also graphs with paths. And that means that the query that returns paths can again be the basis for that query result, can be the basis for a new query. And therefore, then it's closed. The language is closed on this path property graph model. What's also important is that query language for graphs is tractable, because even more so than with relational queries, which can be quadratic very often in complexity, or recursive queries in SQL can even be worse than quadratic, but like join queries can be quadratic. That is already very often a problem for users, in that if they formulate a wrong join query, then the query will not really finish. This same problem you can very, very easily get, and much earlier with graphs, because the complexity of certain operations can really explode quickly. For instance, enumerating all paths, like this all path semantic. I mean, you can have shortest path semantic, you can cheapest path semantic, you can also talk about or think about all path semantics. But if you really want to have the result of a query that asks for all paths between two nodes, even just two nodes, in a quite connected social graph, then this is going to be an extreme explosion of possibilities. That is certainly exponential. But even operations that sound innocuous, like, okay, I only want the shortest path, but I don't want, or the shortest end path, but I don't want any repetitions of edges or nodes in this path, then that's already going to potentially blow up. So simple paths are much more expensive to. So the ensuring of that there is no duplicate vertex or edge in a path is very costly in the algorithms. Yeah, because for shortest paths, you can imagine that you would try to use algorithms like Dijkstra's algorithm. If you want simple paths, then an algorithm like Dijkstra needs much more memory because it has to remember a much bigger state along its computation. But also, like if you talk about regular expressions, certain kinds of regular expressions are tractable, other kinds of regular expressions lead to intractability. Certainly, if you have regular expressions and then you also put in some filtering, so filter conditions on these regular expressions, then it depends on what kind of filters you want to support. Certain of those are extremely dangerous. Okay, so the nice thing about G-Core was that we had practical people, architects, well, people like from industry, people who are more who are scientists like me or more interested in systems architecture, but also some theory people who could help with doing so. Doing so meaning designing a query language that's both functional but still tractable. That doesn't give the user a kind of bomb that will explode so easily, because that is the problem. That for users it can be extremely frustrating that certain queries work perfectly, but then if you change one letter in your condition, then suddenly the query becomes intractable. So you want preferably to give the user something in which, well, it's relatively easy to avoid intractable queries, and in which this is understandable. So, like if you have like a functionality which is in principle intractable, but you only have solutions for certain cases where you can actually return a result on a large graph, then it's really hard to sell this to a user, because it's like in many cases you will actually never get an answer, and in some cases the optimizer can identify, okay, I can use an optimized algorithm and you can get an answer fast. And then the user has to discover which queries are computable and which queries are not computable, which is not so nice. So we wanted to avoid those situations. So here you see a flavor of G-Core. This is a very stupid query. It has this match clause that's for pattern matching. So here we're going to find all persons in a particular graph, and then there is a condition, so a filter condition where employer is Google, and what's returned, what is the outcome of this query is the construct in the construct clause, and here it just says n, which means this graph is going to return only nodes, actually no edges, because n between parentheses stands for nodes. So where the variable n is being bound in the match clause to nodes that have label person, and this query is just returning persons but no edges between them. So it's arguably not so useful, because it's not really a graph. Here you see an example of a join query. So this is actually a value join, and it joins. It's like data integration use case where you would have multiple graphs and you actually are connecting them. Here with join on name is employer. So the names of the companies in the company graph you match with the employer name in the social graph, and then you return the company nodes and the person nodes, and you create a new edge called with the label works at in this example. Okay, so and essentially what the semantics of this is that matching is ongoing. I'm talking about it. Matching is ongoing. It works in two graphs, and you would say it will construct two binding tables. One in company and one in persons, and then you've got like a Cartesian product semantics, just like you have in a relational query, and we are filtering on the Cartesian product, so that's a value join. So we filter with this name is employer condition. And in the end, the last statement is a union of social graphs. So it actually says we are going to do a graph union between social graph and the result of this join. Okay, so we basically add companies to this graph as vertices. So and okay, so here you see what I just said. So you would do matching in C, you get a binding table C, a binding table from N. There is a Cartesian product, and you filter on it, and you get a joint binding table. And this joint binding table effectively drives the construct. It provides the bindings of C and N that will that drives construct to create new works at edges between C and N. Okay. Yeah. So here we see this same query. We see it now working on the original, the example that I showed you before. And what's going to happen here is that, well, this is the query result that's finally being formed. So yeah, we basically have integrated the black graph with the red graph, and we have connected certain nodes with each other with new edges. Yeah, so that's just one example. Another example would be, okay, suppose you don't have the red graph, but you actually have just the black graph. You can actually see that in employer you have a multi-valued attribute called employer. So Celine works for SAP and HPI, and John works for Google, for instance. You could also imagine a query where you want to create these nodes out of thin air, or rather you want to create company nodes but out of values, and that's what this query does. We will match all persons, and then you bind them in variable n, and then you will actually introduce two variables which are unbound, y and x, which just appear in the construct clause. And you're saying, okay, I want this. So wherever you see an unbound variable, the construct will create a new entity, because it's unbound. But you are actually going to do this for every n.employer. And what we are actually doing here, I will actually. So what we are actually going to do is but the n also occurs here in n.employer, and what that means is that all the individual values of this employer multi valued attribute employer are going to be unrolled, and so n.employer is going to take individual values, individual singular values for every for every row in the kind of binding table that you don't see here, but it will be created under the hood. And for every one of those single instances, you're going to create stuff. So you're going to create a y and an x. But that's actually not what we want, because this x is unbound. So we would actually create new entities for every binding that would be generated by this process of graph pattern matching. And this is where grouping kind of, I told you before that grouping is closely related to constructing new graphs. So you actually want to create new companies, but you don't want to create a different company every time. Sometimes you want to let the edge point at the same new company, and that semantics you can get by you have to tell somehow when a company needs to be a new company and when a company needs to be the same company, and that's kind of a group by expression. So here we're going to say, okay, you create something unbound, so x, but it has to be the same entity whenever e is the same. and E is then the thing that we unroll from the employer attribute. Okay, so I think I have an example of this. So we want, do I have this? Actually, I don't. We should have, well, okay, my example is not so good. It would have been better if, would have been better if we would have had a company that actually receives two incoming edges here. Okay, I think I have the old version of my presentation here. Other areas of interest are these Xpath queries. So path queries find their place in principle in matching. So because you're looking for things that are connected by paths. So here you have a query that would ask for combinations of persons N and M that are connected by A paths of knowing each other. And that path can have a length of 0 or more edges. Of course, with the additional conditions that the first name is John Doe and N and M are located in the same place. Where place is actually an empty set of parameters because we're not really interested in binding a variable in this case. Could have had an unbound variable there that's not used in construct, but you can leave it out in G-core notation. So this is a reachability test. So N must be reachable. And this is a existential shorthand, a syntactical shorthand for in fact an existential subquery. So we are actually using in this condition something that you would expect in a match statement. So this N is located in the same place as M is located in. That is actually something that you would expect in a match statement, and the idea is that whenever that returns something non-empty, then this where condition would be true. But you can also take this path query functionality further. So you cannot only ask for reachability. Sometimes you want to actually find paths. In that case, you need to, or you want to find paths, so you need to put in a variable that you are then binding. In this case, there is a variable p being introduced in this slash notation. So it still says no star, but it binds this whatever it finds, it binds it into p. Now it becomes important what the semantics is actually of this path, because was it all paths, was it shortest path? And here we choose for shortest path. If you would ask for all paths, this would be an explosion, because there would probably in many graphs be an even uncountable amount of paths, because if you have cycles, all paths actually means that you have to include every cycle 0, 1, 2, 3, 4, infinite number of times. So this is a really nasty kind of infinite amount of return results that you cannot enumerate. So in this case, if you want to retrieve path, it should be a shortest path query. And in this case, we actually have an n shortest path query. So we ask for the 3 shortest paths to be returned in 3 different bindings in that case. And we also can ask for a cost. So cost by default is the length of the path, so the number of hops. But as we can see, you might also want to be able to specify this. What's further funky about this particular query, which is specific to G-core, I think this 3 shortest path with cost, that's kind of stuff you can also find in Cypher extensions and in GQL proposals. But what G-core supports is this a path in the data model, the path property graph data model. And that is being exercised in the construct clause here, where we are saying, we actually, by saying at p, we are saying, okay, we want to add paths to the result. So to add these persistent paths that are part of the database. So the stuff that we find in P with the shortest path code, the shortest path clause, those paths that we find, we want them to become part of the result graph. So that's how we do that. And we give a local people as a label. We attach a label to these paths that we found, and we also put a property on. This property is called distance here, and we add the the cost to it. So yeah, basically this query will find the shortest paths between John Doe and anybody else who is located in the same place. So you find all those people and then all the edges between those people, and even the persons between those people you have to include as well. But it also adds a list of paths to the path database, database of the result, the resulting graph. Okay, so that's pretty funky. There is more. You would have to read the paper. It contains views. It contains special constructs for modifying properties in things that you result. So you can set them. You can also delete properties, because normally if you return an existing node, it will be inheriting all its properties, but sometimes you want to exclude certain properties in the result. It can have these optional matches, which is also something that is part of a language like Sparkle, of course, optional. So a keyword there. It has roughly the same semantics. And in these expressions, so there is also the possibility to use kind of regular expressions. And what's happening here, so is that you can kind of build more complex shapes or conditions on the structure of the path that you traverse, regular expression like, by defining path expressions. And that's what you see here. So we define something called W nose, and then later we use W nose star. So that's the clean star of W nose in the match statement. So it basically refers back. W nose is not really a label or something in the graph, but it refers back to this pattern. And this pattern you can also use to put in conditions. It can basically define a shape. So now it's between X and Y and edge E at nose, but it could also be a more complex shape. A shape that consists, for instance, consists of multiple edges. So you can kind of say, okay, maybe 2 nose steps, or a nose and a like step, something like that, or a nose and a works for step. And then you can do that on that more complex path, you can do a star, So that's effectively what will happen in the match with W nose star. You can put in filters and also return a cost of this path. So that's where you can actually define things that are different, but the cost is something else than the number of hops. You can actually maybe extract something from a property. Like here we are extracting number of messages, as that's a property of the edge, and we are letting that play a role in the cost of that hop. Actually, here we are trying to say, we do 1 divided by that, because we really want it to be the case that if you have more messages in common with somebody, your distance to that person is lower. So you would actually not sum them directly, but sum the 1 divided by. Okay. Well, in Gcore we also thought about this idea of, our graph query languages may be a superset of relational query languages, because in graph query languages you want all this relational functionality. You want to have where clauses, and you want to have joins. You may actually want to have the possibility to join a table and do data integration between a graph and a table. So the second dot says, okay, you might actually, you have a match that allows you to get a binding table from a graph. You could also allow from, that basically means that every record is a binding. And you can combine the graph part, binding tables, with regular tables, Cartesian products, standard semantics. And what you can also do is you can say, I don't want to return a graph. Maybe I sometimes want to return a table. So then you would say, okay, don't use a select construct clause to construct a graph, but use a select clause to return a table. And the task of the select clause is then to take those bindings, because you have bindings that are nodes and you have bindings that are edges, edge variables and node variables. but you need to translate them into literals that can be seen as a table. So then that's basically selecting a property like a n.name, so the name property of a node. That's something that you could put in a column of a table. That's what the select clause in that case would do. So yeah, that would be a relatively same proposal, we think, to combine relational data and graph data. And you can kind of mix and match. Then you have a query language that's kind of closed on both tables and graphs. And you can return tables and use them in subqueries, and you can return graphs and use them in subqueries. So okay, so the takeaways from GCore were, it's interesting to think about the composition of query language, because then you can do views and then you can do correlated subqueries, and these are powerful things that that have been successful in relational queries. And yeah, you have to pay attention to pathfinding and all that, because it's actually a use case that's very prevalent. And I have to take good care of tractability. Now, okay, so now I will actually skip some of the next slides, because they talk about these other query languages, GCore and Cypher, but well, Dean was so friendly to introduce these. So here are some this explanation of the model and of the return. This is Gremlin. You can see this G.3 notation. And here was a series of queries where you can kind of see how they would be formulated in Cypher, how they would be formulated in Gremlin, how they would be formulated in GCore. But I will gladly skip over these. Some of the things are not necessarily supported in all language. Some of them are really ugly in Gremlin, I think. Yeah, so I will just skip over these details. Roughly speaking, like Gremlin and Cypher are query languages that return tables. Okay, so Cypher returns a binding table essentially, and GCore doesn't. Yeah. Although Cypher, after engaging with LDBC, started to propose changes to actually start supporting returning graphs. And also they started proposing some advanced constructs with to do certain kinds of kind of linear, with width you can kind of do linear recursive queries, so multiple queries after each other. With unwind you have possibilities to deal better with nested data and iterate over the nested data. So you have a list, but here you have a list, but they also use this for paths. You can also unwind paths. So even though paths are not really part of a data model, there's some special data type, then at least in the same query you can unwind the path and then iterate over the vertices and the edges in the path. That's something that they added. And Cypher for a long time, by the way, was very chaotic. So every new version of the query language would be different. There is also in 2018, there is a paper in Sigmat that finally kind of fixed their semantics. Literally, like corrected bugs in their semantics and inconsistency. So in that sense fixed, but also kind of fixed it in the sense that they couldn't change it afterwards so easily anymore, because now they have a formal semantics that defines what Gremlin queries do. But and yeah, they have width, and then now they have also something called call, so which is a bit more powerful version of doing a nested subquery. I will not go into that. So Cypher is kind of okay, popular, has nice syntax, but it got quite ugly in terms of their semantics, because it grew in various directions, and very often things were introduced that didn't work well together. So I think Neo4j is also kind of ready to, well, they are pushing this whole GQL effort, for instance. So they want yeah, they want something possibly cleaner. I can shortly touch upon the landscape. So part of the landscape is also Oracle. Also, Oracle is very strong in this ISO group that defines SQL. It's hijacked it, maybe, if you say. Microsoft is also there, must say, and IBM is there, but Oracle puts in a lot of manpower. They also had their own graph project. PGX is actually their system. They have a distributed version of it as well that scales on multiple nodes or something like that. But I think the more usable implementation is the in-memory graphs.pgx. And they have a query language of their own. It's called PGQL. Yeah, it's kind of aligned with SQL-like, but it added this pattern matching, and the idea of these recursive path queries, and also these they chose homomorphism, not isomorphism. But they here you see an example of these regular path queries. We adopted them actually in Gcore, but they came from PGQL. It's an ID from PGQL. So here you see it as well. So you define upfront a pattern, has parent, and then you can do has parent star, and you can form you can compose more complex regular expressions from that. And the nice part about this is that those kinds of regular expressions are abstractable. So these are relatively computable, at least if you're interested in the shortest paths of those. Yeah, there has been some talk in making the regular expression functionality a bit more powerful. Even there is a proposal called regular expressions with memory. We will not go into it. It would allow for some more conditions to be added to this. And I basically want to say that this regular expression part originated in Gcore, but also in GQL later. It originated from the Oracle work. Then GSQL, but that's all I want to say about Oracle. Then there's Tiger Graph. So Tiger Graph also stays closely to SQL, but they put a graph sauce on top of it, GSQL, and what their main innovation are so-called accumulators. And so what they actually want to do is they want to make it easier to write algorithms like PageRank in a query language. Because PageRank and those kind of graphalytics or graph analytics usually are more algorithmic, and you would write them maybe in C++ or in some Pregel-like system, but you cannot so easily write them in a Cypher or system, or even in a Gcore system. And they meaning Tiger Graph, they designed GSQL to be able to do some of that using this idea of accumulators. And what an accumulator is you can think of it as a temporary weight or a temporary property that you attach to a graph that already exists. Like if you are computing a page rank in a graph, it would be the rank of the importance value of every vertex that's being updated in the page rank algorithm every iteration. Every iteration you look at all the importance of all your neighbors, and that's part of that you add to your own importance, and this you do a number of those iterations over the whole graph, and finally, well, hopefully this converges to some kind of value, and that's then the page rank. So the idea is to add these kind of the values that you compute as accumulators, temporary properties that hold the data value and that are being updated by a query, and this query is run a number of iterations, a number of times after each other, and this data value is efficiently kept, somewhere and being updated at every query, something like that. So for instance, here you would have maybe a graph with customers and products, and attach. What do you attach? In this case, you would attach. You might want to compute the revenue in this case of the P sales, C sales. Yeah, you want to add P sales and C sales here as accumulators to these graphs, and run this, and at the end you extract the computed P sales and C sales as the query results from your computation. And here you see piece of code that actually shows a while loop. In the while loop there is a query, and this is an implementation of their page rank. Okay, so where they would, I basically just describe it to you. So that's the idea of accumulators that's being pushed by Tiger Graph. Okay, now we get to the final two query languages. So what's under development? I'm running slightly a bit late. I will finish in 5 minutes by going straight through this, describing it from a high level. So there is this new SQL standard. So the SQL standard people have decided that the next SQL standard's main addition will be graph functionality. And so what they want to be able to do is to say, okay, you don't need to have a graph database, but you can have a SQL database. And in a SQL database, you can store graphs. I kind of said this to Dean as well, like you can see a graph as a table V and a table E, a table with vertices and a table with edges. And so that's what SQL PGQ allows you. There's some syntax where you can say, oh, this table, you can see it as the vertex table, this table, which contains kind of links between end-to-end links between those vertices. You can see this as an edge table. And now you can do graph pattern matching, but potentially also, also shortest path finding, fixed length and variable length pattern matching. So you can do also shortest path queries over those imaginary graphs. The graphs are in fact tables, but you can view them as if they were graphs. So that is the idea. So you would have here, an example. So students, you have a table of students, you have a table of universities, and you have the end-to-end relationship. The students study at universities. Well, you can see that as 3 tables, but you can also see it as a graph. This extension allows you to explicitly identify it, and then you can do some of the things that I discussed for Gcore, specifically also these path expressions. You can use them, and graph pattern matching, very much in the same syntax as I discussed, to discover bindings. And a binding, of course, is just a table. So that fits again in the SQL model. So I will not say anything more about it. I hope you get the idea. You see it. Here's the syntax. So create property graph, and then vertex tables, edge tables, and then you name relational tables and their keys. And from there on, there is something called the student network that has persons, universities, and certain edges, and you can query them with these kinds of syntax. So I'm not sure if this is going to be, if you like it. It's at least less bad than SQL XML. If you remember, that was another creation of this ISO community. But there you would have Xpath, like XML queries in a string. So this is not in a string. This is still parsable. So at least that they got better. And this is an example that is too complicated. And finally, this same ISO working group that's doing this language definition, it is dominated by Oracle, but it also has this Microsoft, etc., IBM people in it. Now there are also considerable Neo4j people that have joined the Swedish National Standards Association, and they are part of this ISO. And Tiger Graph the same. And they are working on GQL, which is going to be this new property graph query language that takes IDs from Cypher, from PGQL, and from Gcore, and it's going to be a superset actually of what SQL PGQ does. So the things that PGQ does, which is basically the path expressions and the graph pattern matching, is part of SQL PGQ. But on top of that, graph construction will be mainly added, but also updates on graphs and recursive graphs. So they are talking about this. And this is some pieces of slides that are coming from the Neo4j side, and it looks quite a bit like Cypher. One of the things that Cypher has always done is it reverses this order. So it starts with the from and it ends with the return, which in SQL will be the select. So what you're finally returning. So they have always worked with this reverse order. They say it's the natural order. In some sense, it may be, because maybe that people think like that. You start from somewhere, you do some operations, and in the end, you return something. So this is not yet fixed. So there is lots of discussion still. I will skip over that. This is also, this BNE 023 refers to a document that's currently out that describes a current proposal in GQL. They have some fancy ideas about multiple graphs, unifying graphs, being able to combine graphs in graphs views. There you see an example of that in this slide. And if you want to know more, we should maybe talk about it. Graph views here. But there's no time. But I hope you get the gist, and also a bit of an overview of the political landscape. So this is something that's ongoing. And this is the same group of people. They are responsible for this extension of SQL, but they are now continuing to do this superset, which is going to be GQL. I think I should leave it at that.